works fine. Okay. So today we're going to talk about molecular bonding. I want to talk about it. Will it let me talk about it? Yes. Okay. Molecular bonding. So this is as opposed to the ionic bonding we've been talking about before. Okay. And I think it's best to start with an example. And I think the first example we'll go with is hydrogen. So in nature, hydrogen comes to us as a gas like this. Okay, this is how it's found, H2. You can look at the Lewis structure of hydrogen, and you can look at the Bohr model of hydrogen. The Bohr model is like this, 1 proton, 1 electron. And we know that in order to have this shell be full, you need to add 1 electron in, right? That shell is full when it has 2. When it's full, it's stable. Helium, next element up from hydrogen, has a full shell, and it is stable. So if you happen to have 2 hydrogen atoms nearby each other, and they would both like to achieve, I shouldn't say like to, they were both stable by adding an electron, you see that, you know, if one loses an electron, you end up with an ion and then another ion and a full shell. And that was sort of how ionic bonding worked. But in the case where both need an electron, you can't do that anymore, right? So you end up with the scenario of molecular bonding. And what happens in molecular bonding is these electrons become shared pairs between the two. So if you imagine that this is the shell of the first hydrogen and this is the shell of the second hydrogen, these shells essentially link up and act as if they're both 2 full shells, and those electrons exist as a pair of shared electrons. And what we've created here is a bonded molecule. Okay, this type of bonding is called a covalent bond. All right, it's very different than an ionic bond. Well, that's sort of a lie. It's not very different. It's kind of like a range between what's ionic and what's molecular, but this is basic, so we'll just say for now, for the sake of an understanding here, that these are shared between these two equally. And in the case of a hydrogen and a hydrogen, they actually are shared equally between the two. All right? So this is considered a covalent bond. We'll draw a couple of more scenarios where we would make a simple covalent bond. Like, for instance, all the halogens form binary compounds too. So for instance, let's talk about fluorine. Fluorine comes to us in nature like this. And if we draw the Lewis dot diagram of fluorine and its electrons, we'll notice pretty quickly that fluorine, I'm going to draw that as next there, that each of these fluorines, you know, needs an electron or attempts to gain an electron or tries to pull electrons towards it due to something called electronegativity. Again, not something that we need to discuss right now. But you can see that this is another scenario where we're going to have sharing, right? 2 nonmetals, each looking to gain electrons, each pulling electrons towards itself, and you end up with another scenario of shared electrons. So we get a bond like this. Okay. And I call this a Lewis workup. I'm not sure if that's exactly the correct name for it, but it shows the Lewis dot diagram and it shows the shared electrons. And what we'll usually do is actually draw a ring around each one of these fluorines like this. And we'll see that these are shared. They're kind of like a Venn diagram. They're in both fluorines shells. Okay. And this is, again, the creation of a covalent bond. You with me? Now let's get a little more complicated here. Actually, let's write a couple of notes about what we noticed here. Okay, so covalent bonds are formed between two non-metals. Okay? The result is the formation of entities called molecules. It's not very good writing. Let me fix that. Okay? Covalent bonds are formed between two nonmetals. The result is the formation of entities called molecules. So if we just scroll back up here, if we have a whole bunch of F2, a whole bunch of fluorine gas, basically it consists of a whole bunch of little individual chunks that sort of zip around and are more or less independent of one another, at least in the gas phase. Okay, so chlorine is a gas. The chlorine molecule, chlorine is two. I'm talking about fluorine though. Fluorine is a gas, and there's very little attraction between the fluorine molecules to one another. Now contrast that with something like, say, sodium fluoride, which, if you remember, is made up of positive and negative ions arranged in like a regular matrix. Okay, so a completely different type of substance comes from that, and this is why molecular compounds can really have any phase. So here we have molecules that have very little attraction to one another. They're in the gas phase. We'll do an example of water in a minute. Water has a higher attraction, so it's in the liquid phase. Something like, say, sucrose, like sugar, actually is a molecule, but it has enough attraction that it crystallizes and it's solid at room temperature. So molecular compounds can really be in any phase. Ionic compounds are nearly, as far as I know, always found in a crystalline or in a solid stage. Okay, so that's a big tip-off, or one of the big differences, I guess, between the two types of compounds found in nature. So they form between two nonmetals. The result is the formation of entities called molecules, right? What are molecules? Well, they're discrete particles. Molecules are discrete particles. Do you know what discrete means? Like, they're like individual, like measurable entities that are separate from the whole. Like, each of you is a discrete individual in a class. Okay, each molecule is a discrete entity in a volume of gas. Does that make sense? Okay, something to say about covalent bonds. Well, actually, let's do another example, and then we'll say something about covalent bonds. So let's say we have an oxygen atom. We've all probably heard O2 before. So oxygen comes as two oxygens bonded together. Each oxygen has 6 electrons in its outer shell. Now the question is, this guy needs 2 electrons and this guy needs 2 electrons to fill the shell. So if this one needs 2 and this one needs 2, that means this will have to share 2 with this one, and this will have to share 2 with this one. And this forms something slightly different than what we've seen before. So let's look at what happens here. So if these electrons adjust themselves, so they're like this, you can probably notice that if we ring these up, 2, 4, 6, 8 on this oxygen, 2, 4, 6, 8 on this oxygen. So now each of these, if they share 4, ends up with the total amount that they need around them. But if you look, we're now not sharing 2 electrons, but we're sharing 4 electrons. Okay? And while we're on this topic, let's look at one more thing that comes as a binary molecule, binary molecular element, and that's N2. Okay, so if you look at nitrogen, nitrogen has 5 electrons around it. Okay, so in other words, each nitrogen needs 3 electrons to fill its outer shell, right? In the example of oxygen, when we needed 2, well, each had to share 2. Now what do you think? Each would have to share 3 electrons between them. And that's exactly what happens. So you end up with this kind of a scenario. 1, 2, 3. And then it's still got 2 more, 4, 5. And then you end up with 1, 2, 3, 4, 5. And we have to put them in their circles to see where they are. 2, 4, 6, 8. 2, 4, 6, 8. Okay. And now we've shared 6 electrons. Okay. Now don't worry. This is the maximum number that you can share. What I want you to notice is a couple of things. The first is that we always share in multiples of 2. This is called a single covalent bond. This is a double, and this is a triple. Okay? So I'm going to write a note about that. There are 3 types of covalent bonds. By the way, look at the word co and valent. What does the word co mean? Together, right? Like if you cohabitate with someone, you live together with someone else. Your co-workers are people you work with, right? Covalent, well, that means together in the valence shell, right? It's in the word that's indicating what's going on here. We're sharing electrons in our valence shells. So these are covalent. Think of them like roommates, right? Or pals, or like, best buds. Yeah, they valent together, They just hang out and valent away. There's 3 types of covalent bond. Single, double, triple. The other thing to notice is that covalent bonds always have multiples of 2 electrons. So what that really means in practice is a single bond will have 2 electrons. That's a single bond. And that's 2 shared electrons. 4 shared electrons is a double bond. And 6 shared electrons is a triple bond. There is no such thing as a quadruple bond. There's only a single, a double, or a triple. Okay? Let's do another example. And I think, looked at this the other day. Let's look at how H2O would work, right? Because it's not just bonding between the same elements that goes on. There's also bonding between different elements. Let's do H2O, and let's also do CH4, okay? Notice no metals are involved, right? So we know we're dealing with covalent or molecular substances when there's no metals here at all, right? If we have metals, that's ionic bonding. That's what we took first, okay? So if you look and you don't see a metal, you know you're dealing with a molecular compound. So if we look at oxygen, okay, oxygen has 1, 2, 3. What am I doing? 4, 5. Sorry, lost my train of thought there. There we go. 6. Okay, and then hydrogen has 1. Okay, and there's going to be 2 hydrogens because oxygen needs 2 to fill its shell. These are going to share between here and here, and these are going to share between here and here. So if we write our circle around here, we've got our one shared pair there and our one shared pair there. Okay? This is how a water molecule is created. All right? Now you might wonder, why is it that water is liquid? Why isn't it a gas like fluorine was? The secret to that goes a little beyond this course, but let me just ask you this. What type of charge do electrons have? Negative. Okay? So there's there's a negative center here, a negative center here, a negative center here, and a negative center here. Well, there's also no electrons out here. So what ends up happening is that you get a molecule with a polarity to it. Do you know what a polarity is? Like essentially a positive and a negative end. Don't worry about these symbols. But if you can imagine now a whole bunch of waters, the positive end of the next water molecule will attract to the negative end of this water molecule. So there'll be a stronger attraction between water molecules than there is between fluorine molecules. We learned in our lab the other day that if there's a stronger attraction between things, they tend to be more towards the solid end of the spectrum. So a liquid is more solid than a gas, and a solid is more solid than a liquid. If you cool water down, you only have to get to 0 degrees Celsius before it becomes solid, and that's because it stops jiggling enough that these attractive forces lock it into place in a solid. Okay, does that make sense? I think it's a sigma symbol. I think it's like a baby sigma. You don't have to really worry about that. That's just some extra learning. That's not part of the course. But if you take, it's a Greek letter, Greek symbol. Anyway, let's go over to carbon and 4 hydrogens. And let's see if you guys can do this one on your own. Can you make this work for carbon and hydrogen? All right, so methane. We got to look at carbon here, and we'll notice pretty quickly that carbon has a Lewis dot diagram that looks like that. We know from experience at this point that hydrogen has 1. We see in the chemical formula that there's 4 hydrogens, so each hydrogen, hopefully it's clear, is going to pair up with each of these unpaired electrons on carbon. And if we throw in our shells here, we can see that everybody's shell needs are satisfied. Okay? So there we go. 2, 4, 6, 8 around carbon and 2 around each hydrogen, and everyone's happy. No. This is new stuff. Okay, now let's draw this. What we've been doing, these are called Lewis workups. But it would be kind of like annoying to have to do this every time. So there's a simplified version, which is called the skeleton. The skeleton drawing. Yeah, it does sound cool. These, by the way, what are these called? What's that called? It is water, but what is this this way of drawing chemical symbols? I think I'm overthinking it here. These are called chemical equations. Wait, no, they're not. What am I talking about? Chemical formulas. Sorry. Chemical formulas. Okay, so chemical formula, Lewis workup. Let's do the skeleton drawing. So let's take water. Okay, so how the skeleton drawing works is electron pairs are shown with lines. Okay, so if those electron pairs are bonding, then they're shown as a line between the 2 atom symbols. So for water, that would be like this. And you've probably at some point seen a symbol that looks something like that. Now, some people don't draw the unpaired electrons in, but I definitely prefer that. So electrons that are not involved in bonding, but that are still there, we draw as little hats or caps. Okay? So they're not connecting 2 elements, but they're still there, so we just draw them. These symbolize electron pairs. So then if we went to over to here to methane, it would look like this. Okay? Each bond is a line connecting the two elements. Since there's no extra electrons out here, we don't have to do any bars. Okay? I'm going to get you to try one more. Try making carbon tetrafluoride. So CF4. Can you do it? Okay, so if you have a look here, you got your carbon, and it has its 4 electrons here drawn as circles. Fluorine has 7. So what ends up happening is carbon shares 1 with each fluorine, and fluorine shares 1 with each carbon. 4 of them. You end up with 4 chemical bonds and 4 fluorines around there. So that's our Lewis workup, and then our skeleton formula just looks like this. Okay, good. But you can't forget that there are these non-bonding electrons around, and we want to talk about them. So you got to bar them all up. And this is, I think, the preferred way to draw a skeleton formula, showing all the electrons involved. Okay? And that is where we're going to leave it. Next time we'll look at polyatomic ions, okay? Which are essentially just molecules that needed to borrow some electrons.